So in the next couple of slides, I just wanted to explore some of the ways that people have used clouds, and one obvious way is using clouds to run the applications. And so this would mean that I take my more traditional application, and I'm calling it HPC here, but it means more traditional computational application, and then run it on EC2 or Azure or some cloud platform, right? There are advantages to doing that. I can, if I have a credit card, I can use EC2 quite simply and run my application. And if my application has the right characteristics, I can do very well with that, right? So if I have an application that has very little communication requirement, that's pleasingly parallel or embarrassingly parallel, I can get very good results. It doesn't do much I/O. Right, so I can scale up very nicely, and it becomes a very effective way of running my applications. And in the early years with cloud computing, you saw a lot of application migrating and using platforms such as EC2 to run their applications. And as I said, while this works very well for certain classes of application, there are application classes that this direct migration to clouds may not be the most effective. And then many reports point out that even though the cost per CPUR tends to look quite reasonable, these costs can add up very quickly because of the scale of the science as well as the experimentation process that goes with a lot of these applications, right? And there's a very interesting report that I think you're going to hear about later in this, or might already have, the Magellan project. And these are some numbers from there. In their experiments, they found that baseline clouds are about 8 times more expensive, and effective performance of the cloud is about 16 times less specifically for the DOE mid-range HPC workloads. And the plot on the right shows basically the EC2 time, a ratio of the EC2 runtime and the Magellan runtime, and you see a slowdown for many of the applications. Exception there is BLAST, which is a very nicely parallel application. Now granted, these are very dependent on the type of instances and that you use on Amazon, for instance, and there are more sophisticated, more computational friendly resources that are available at Amazon and other cloud providers now, and so these numbers might, but they're more representative if you just take a vanilla instance on a cloud provider and ran your resources, what one might expect. So what we were trying to do in some of our work, and what other people are trying to do, is to see, this is a nice experiment to run your application of clouds, but can we think beyond these obvious candidates? For example, clouds tend to, rather than guarantee reliability and assume that faults don't happen, which is traditional for a lot of the supercomputing platforms, clouds tend to give you a lot more flexibility and scalability, but do not provide the same level of guarantees, or one cannot make the same assumptions in terms of reliability on cloud platforms. And so this would mean that one would have to come up with more interesting formulations of applications that are asynchronous or resilient to latencies, data loss, failures, and the like, right? And so if clouds are the target platform, coming up with interesting formulations that have these characteristics becomes important. And interestingly enough, this formulation can also then tend to perform better on more traditional infrastructure itself, because they tend to reduce communication and these aspects that can be expensive. Right. One can also think about new usage modes where you have a client and a backend that runs on a cloud accelerator. For example, you could think about more analytics packages or spreadsheet type packages that have Amazon EC2 as their backend, where they run the services. So you do a large-scale analysis, and that gets run on an appropriate number of instances of EC2, and is able to do large-scale analytics from your desktop or your handheld or some device. And then one can think about end-to-end application workflows that have components that are more suited for HPC's environments and grids, and then there could be other pieces of the workflow that would be more suited to clouds. For example, you could do a lot of small experimentation on clouds, and which tend to be more quickly accessible and more readily accessible. And then once one knows what are the interesting parameters, one could do more extended runs on an HPC or a grid type environment. One could use this for doing online analytics on data. One could think about doing this to do parameter estimation using cloud type environments, and then doing your more production runs on the HPC or grid environment. So one can think about workflows that are more appropriate for a hybrid grid plus cloud environment. So in our study, we really tried to look at three different usage modes where one could think about integrating clouds and CI. And there's a recent technical report that is linked from the website, which gives a lot more detail into these three modes. But the first mode was HPC in the cloud, where really what you're doing is trying to outsource entire applications to current public or private cloud platforms, right? And this was analogous to the first example that I gave, where you have your entire BLAST application or some application that you run on EC2 or some other cloud platform. Right? A second mode is a mode where you use HPC plus clouds. And here is the mode where I was talking about, the hybrid cyber infrastructure, where clouds can complement more traditional resources, providing capabilities for acceleration, to support spikes, to support specific requirements for software or hardware, right? So they can become providing complementary capabilities as part of a hybrid cyber infrastructure. And finally, what I haven't spoken about is really exploiting the elastic nature of clouds, and the idea is to use software layers that make more traditional grid or cloud infrastructure accessible using HPC infrastructure accessible using cloud abstractions. And the idea is to combine the flexibility, ease of use of the cloud model with the specific capabilities and performance that an HPC platform provides. For example, in some of our work, what we have done is try to add software that can use a federation of Blue Gene supercomputing systems, the IBM Blue Gene system, as a cloud, so as an elastic as a service resource, where applications can scale up or scale down or scale out to other Blue Genes, just as the way they could do with Amazon, right? And so what that does is it reduces the barrier to access these resources, and that's what we're calling as HPC as a cloud. And there's similar experiments that people have done on other such platforms as well, right? And so that's another way one could use the cloud abstraction to support science and engineering on these platforms.